So welcome back, everyone. So we'll start the afternoon, or actually we have only one talk this afternoon. So we'll have Carlos's third talk on the moduli of local systems, the Dolbeault approach.
Okay, so thank you very much. So in fact, let me start by the thing which I was doing at the end of yesterday's talk. So let's start with some geography from yesterday. So this is the question. So let's suppose X, for example, X and P3 a hypersurface, a surface, in fact, of degree D bigger than or equal to 5, so it's of general type and very general. Well, let me just say a word about D equals 4. So in the case D equals 4, sorry about that, but in the case D equals 4, it's a K3 surface. And here Yoshioka, I should probably say Mukai and Yoshioka. Look at the moduli space, and because it's a K3 surface, then there's a Poincare duality for the cohomology. That makes it so that it's going to be smooth. So all the components, it's always good. So smooth, and in fact, yeah, generically smooth of the expected dimension. Okay, so for D bigger than or equal to 5, then what I mean here is, of course, the moduli space on X of degree. Let's look here, 2, C1, C2. This is true for rank R. The moduli of stable bundles of rank R degree and given C1 and C2 is always good in this case. So for D greater than or equal to 5, then we know that if by O'Grady and everybody else, which I said, this probably follows from somebody's previous version, but the O'Grady's theorem is the definitive version of this. If C2 is very big, then we know that I should say good and irreducible. So from the point of view of Donaldson invariance, this really means that this is a perfectly good thing on which to define Donaldson invariance. Okay. Good and irreducible. Shall I just recall, good in this context means generically smooth of the expected dimension. That's equivalent to saying that generically, at a general point of the moduli space. So if E general point of its component so if the moduli, if you don't know the moduli space is irreducible, then goodness is a property of a particular irreducible component, okay? So if E is the general point of its component, then the abstraction space, which is H0, Sarvaswara nicely explained this, H0 of E, of end E, let's say trace 0 part, tensor Kx equals 0. This is the dual of H2 of endomorphisms. This is the obstruction space. By Serre duality, the obstruction space, so one should say, but when we talk about the expected dimension, a little detail here. When we talk about the expected dimension, we count using the trace-free endomorphism because there's going to be a H1, I think, or something like that of OX, H1 and H2 of OX, which are not going to count there. So for the expected dimension, we're using the trace-free endomorphism. Since we're on a hypersurface, H1 is 0 and so on, so there's no, the determinant can't vary, so. Okay. So let me just make a side remark here, which is kind of interesting, which is that you'll notice that the space of obstructions to deforming is an element of H2, is H2 and 0, but by Serre duality, the dual of that space is H0 and E tensor Kx. So a co-obstruction, so for curves, a Higgs bundle, we'll see in a minute, is a point, the point is a point in the dual of the tangent space. So here we have like a Higgs, this is like a space of Higgs fields, but it's the dual of the obstruction space rather than the dual of the tangent space. So a dual vector to the obstruction space can be viewed as a Higgs, some kind of Higgs field. And in particular, but this is like this is a good kind of Higgs field because it has coefficients in alignment in the canonical sheaf, okay, instead of omega 1x. So I think this is an interesting theory of Higgs bundles in some way. Sometimes people say, okay, this was Kapustin-Witten or something like that did some kind of gauge theory for that. Sometimes I have a hard time finding that reference, so I'm not completely sure whether if there is or not some gauge theory for this type of thing, but possibly. Okay. And so you might say the question is what happens by Bogomolov-Gieseker. C2 has to be, let's say delta. The delta invariant has to be strictly positive because there's no flat bundles. Except maybe, so there's a case of degree 0. If it's degree 0, then you can have the trivial bundle, but let's not count that. So basically, delta has to be strictly positive. So between delta strictly positive and case C2 large, then the question here is, what happens in between? Okay. And so we worked on this with the Nicole Astrano. We looked at the case of surface of degree 5. So X is a quintic. So let me just kind of briefly, and this is what I wanted to say here, explain how that goes. So for C2, so in this case, so let's, and we're going to take C1 equals O of 1. So let's notice that Kx here is Ox of 1. So this is like as close to being not of general type as you can get. So this is some kind of variety which is just slightly of general type. Okay? Yeah. Yeah, if you want, okay. Yeah, no, okay. But for odd degree, we're only looking at odd degree, and that's a big question is what happens for even degree, I think. We don't know. But for odd degree, then you can't have a projectively flat bundle, I mean, if you think about it. And it turns out that in fact C2 but let me just say this. So for C1 equals this, then the delta is equal to the C2. I mean, well, no, not really, but, well, sorry. But then, like a first observation is that in fact, that C2 is bigger than or equal to C1 squared is like a quarter or something like that. So, so it's basically delta and C2 are pretty much the same. C2 is bigger than or equal to 4. So then there's this guy Nice. Since we're in Nice, it's good, right? But it's spelled like that. Nice was a Nice, something, or I don't know how you pronounce this, but he was a student of O'Grady. And he has a paper which proves, this is from like the 1990s. He proves goodness, I think for C2, if I'm not mistaken, bigger than or equal to 16 or something like that. But particularly, he also proves an important result which we'll need. Nice's connectedness theorem says that the M bar thing, and we're also doing rank 2. The M bar thing is connected. For C2 at least 10. In other words, each component meets the boundary. And this is an application of O'Grady's techniques. O'Grady has a main technique which involves restriction to a curve and looking at the map, the birational map to the moduli space of sheaves on the curve. And by some kind of dimension estimates and intersection of the theta divisor and stuff like that, you can conclude sometimes that that birational map has to be a birational map. It can't be an actual map. And in that case, when you work that out, it leads to a way of deforming your bundle to a torsion-free sheaf. The fact that that map is birational and not an actual map corresponds in some way to getting a deformation to the boundary. That's it. In a nutshell, O'Grady's techniques. Okay. And so for C2 less than or equal to 9, then by Euler characteristic, Sarabaswara discussed this yesterday. By Euler characteristic considerations, we get H0 of E different from 0. So it means that E fits into an exact sequence like this. Right, the determinant of E is O of 1. And so what's P? Well, any kind of subscheme, so this is the ideal sheaf of a finite length subscheme. Kind of by definition, E is a rank 2 bundle which is generating the ideal. So by definition, pretty much, that means that P is a local complete intersection. I mean, locally it's generated by the two sections of E. E is a rank 2 bundle here. So it's locally complete intersection subscheme. And now the other kind of general theory thing, which everybody should know, is Serre's construction. Which in more recent times was notably used by Igor Reiter. In his thesis. He was a student at like a year ahead of me or something like that. What does that say? That says that you have an exact sequence like this. If and only if P satisfies what's called the Cayley-Bacharach condition. So yesterday was going to be Cayley Day, but it turns out that now I'm doing this today. But this was supposed to be yesterday, okay? So it was Cayley Day, right? As you'll see in a minute, even more so. So what does it say? It says that for any co-length 1, sorry, I should say for sections, in this case, of OX of 2. This is like the 1 from here plus the 1 from the KX. Right? The 2 there is the 1 here plus the 1 from KX. By the 1 here, it means the difference from that and that. So if this was O of minus 1 to O of 2, that would be 3 plus 1 is 4. Okay. What does this mean? It means for any co-length 1 subscheme, P prime inside P, and I should point out here that this local complete intersection property, in particular, it's Gorenstein. This is important here because it tells you that at any given scheme theoretic, set theoretical point, there's a unique co-length 1 subscheme. Because there's a thing about the Sokol filtration, it's not the same Sokol, but there's a thing about the Sokol of a Gorenstein local, of a local Gorenstein ring. So a Gorenstein local ring, at least in dimension 2, on a surface, has a unique length 1 ideal. Like the bottom of the thing. I mean, the picture kind of looks like this. I mean, if we sort of take, if we take x to the n, and if you take, x to the n and y to the m, right, then kind of the picture of the subscheme, you might say, of the monomials in the subscheme looks like that. And this is the unique monomial. This is the unique ideal of length 1. So at each point, there's really only one possible choice, but this means we choose one of the points and then take that thing. So for any co-length 1 subscheme of this thing, the map, if you take the diagram H0 of OX of 2 into OP of 2, then we restrict to OP prime of 2. This doesn't have to be surjective. We look at the kernel of that and then the kernel prime. The statement is that these two kernels are the same. Okay? Which is as equivalent to saying that really this map here, the map of the quotients, is not surjective. Saying that the kernels here are the same is equivalent to saying that the map of quotients is not surjective. But saying that these two kernels are the same, that means that the conditions imposed of vanishing along P on degree 2 forms is the same as conditions imposed on vanishing of P prime. Or to put it another way, if you have a quadratic form, if you have a section of O of 2 or a quadric, which vanishes on P prime, then it has to also vanish on P. Okay? So, okay, that's the condition. So this is an important thing to understand when we're looking at, if you're trying to, at least for rank 2, so how this works in higher rank, I'm not really sure. That seems a little bit more intricate. I mean, it should be kind of similar, but for classifying rank 2 bundles, for low values of C2, you have to use this principle all the time, basically. This is like the basic working tool of the whole situation. That's essentially because we're going to have an exact sequence like this, where these two pieces are not too far apart and P is not all that big. In this case, the length of P is going to be equal to C2. By length, this means the length, right? Okay. And so then what can we say? So let's just do by hand the case of length of C2 equals 4. Right, so we have a subscheme P inside X, which is contained in P3, and it satisfies Cayley-Bacharach of 2, right? So it says that any 3 points, this is 4 points. Any 3 points So vanishing of a quadratic Q at any 3 points implies vanishing at the fourth point. Okay. Now, how can this happen? So there's if the 3 points, if we have, if our 4 points are not contained in a line, then we could take a line going through 2 of the points, and some other line going through only one of the other points, but not the other one. Okay, that would be those 2 lines would give you a quadratic. I guess I'll say any. Sorry. What should I say? I mean, we could even take a plane that passes through. If they're not coplanar, you could take a plane that passes through 3 but not 4. That would even be a linear form that doesn't satisfy this. Suppose they were coplanar. Then in the plane, we could take a line that passes through 2 and a line that passes through one of the other ones, but doesn't pass through the fourth one. That would contradict this condition. So this implies that the 4 points are collinear. But since now P is contained in the surface, so that means that P is contained in the line. This is the line inside P3. Intersect the surface. The line intersect the surface is 5 points. So it means that the choice of this exact sequence is equivalent to taking a line and choosing 4 out of the 5 points. Well, it turns out that the extra point is equal to the point where E is not generated by local sections, by global sections. The extra point in the line, there's 4 points, and then there's a 5th point in the line. That's the point where E is not generated by global sections. And so it turns out that the moduli space is actually, the moduli space is rank 2, degree 1, C2 equals 4. This is actually isomorphic to X, okay, via the map given by this point. So the thing is that for a given bundle, several different lines might give you the same bundle. The choice of the line, that depended on the choice of a section. Right? The choice of a section wasn't unique. So the subscheme, if there's several different sections, you might have several subschemes. And let me just sort of finish this discussion by pointing out that for C2 equals 5, then by the same argument, P has to be equal to L intersect X. But in this case, there's another point. In this case, it turns out that E is actually equal to R restricted to X, where R is given by the resolution of the ideal of a point, I guess. I'm not sure about the degree here, but something like O of. There's some point y. There's some point y in P3 where, if I'm not mistaken, you take the ideal sheaf of that point, you generate it, you try to cut it out by 3 in P3 by 3 hyperplanes, and then there's a kernel which is a rank 2 sheaf. This is rank 1 and rank 3. The kernel is a rank 2 reflexive sheaf on P3. But if that point is not inside X, then R restricted to X is a bundle. And that's going to be the case of C2 equals 5. And so you can see that, in fact, M4 sits inside M C2 equals 5 bar. That's equal to P3. This is equal to X. So here you can see explicitly the moduli space of bundles, which is, so M of C2 equals 5. That's equal to P3 minus X. And its boundary, so its boundary where the bundles degenerate to torsion-free sheaves is the case where the point Y moves over to X. When point Y moves over to X, the limit of this R restricted to X is a torsion-free sheaf, then the associated reflexive sheaf is the one you get here. Anyway, so you can go on like that. So in fact, so let me just finish this segment of the talk here, actually. So you can classify all the explicitly. This I should point out is some work. In particular, a couple of the problems, there's two problems I was telling Sarbasoir, essentially the two problems that one has to be very careful with, but which turn out to be okay in the end usually. There's one of them which is that you don't know that the subscheme P consists of distinct points. It could consist of, it's conceivable that for some whole irreducible component of the moduli space, the subscheme P always has some higher multiplicity. And the other problem is that the X group governing this extension might have dimensions that jump. Okay. So in this whole thing, you have to be kind of careful. But those are the two main things you have to be careful about. And so the question is just kind of geometry of the Cayley-Bacharach condition. And this kind of illustrates the general principle. So the kind of the general principle is that when something is Cayley-Bacharach, it's sort of Cayley-Bacharach for some reason. So maybe I should have said this. Let's understand why, if we take 4 points inside a line, why is that Cayley-Bacharach? Right, so what a Cayley-Bacharach says, if we remove one of the points, so now we have only 3 points on a line, and if we take a degree 2 form, well, a degree 2 form restricted to a line, that's just a degree 2 form on a line. It can only have at most 2 zeros. So if it has 3 zeros, then it has to equal 0. And so it has to be 0 at the 4th point. That's like the typical argument that's happening in this situation. Okay. So that's why 4 points on a line are Cayley-Bacharach. And so you go along. So let me just write down what happens. So first, we've seen C2 equals 4, C2 equals 5. C2 equals 6, this is P, is contained in a plane quadric, plane conic, intersect X. So if you take 6 points in a plane conic intersect X, I lost my piece of paper with the writing this down, but I think this was correct. For C2 equals 7, this is P is in general position, it's points in general position in a plane intersect X. And here we get to Mr. Cayley again, which is that for C2 equals 8, the general point of the moduli space, and so I should maybe say it's always irreducible, just by explicit calculation. For C2 equals 8, this is kind of interesting. This is what's called a Cayley octet, so P is called a Cayley octet, which is to say it's the intersection of 3 quadrics. Equals 8 points. And then the P's that occur we have our degree 5 hypersurface. Of course, if you take 3 quadrics in general, that'll be 8 points, but which won't necessarily be contained in X. It's all the cases where those 8 points happen to be also contained in X. If you think about it, so you can do this exercise, it's kind of fun. If you remove one of those points, so you take only 7 of those 8 points, and look at what quadrics that vanish on those 7 points are, those quadrics have to also vanish on the 8th point. Okay? They have to be in this linear system generated by those 3 quadrics. That's the Cayley-Bacharach condition. Then for C2 equals 9, wait, do I remember what this was? I think I might be mistaken here, as I said, I lost my piece of paper. I think it's that P is general inside a quadratic intersect X. Then for C2 equals 10, we proved that that E has to, a general point E has to have HI of E equals 0. C2 equals 10 is kind of a pivotal point in the whole situation in the sense that it's the place where the Euler characteristic allows this to happen. I mean, the Euler characteristic advantage is that C2 equals 10. So it turns out that a general point has semi-natural cohomology, or it's like arithmetic Cohen-Macaulay is maybe the usual term for that. And then let me just finish this section by just pointing out that, so then our theorem is in fact, it's always irreducible. So putting all this stuff together using Misse's connectedness theorem, and doing a little bit more work using the boundary and so on, you can get that it's always irreducible. So our theorem is that for D equals 5, a very general X, then M of 2, 1, C2 is always irreducible. Irreducible for C2 bigger than or equal to 4, and good for C2 bigger than or equal to 10. And as Sarbeswar pointed out, we gave an example for C2 for degree equals 6, where M of 2, 1, C2 equals 11 is not irreducible. Somebody wrote a paper, I forget who, called Murphy's Law, which says that anything that could possibly go wrong will go wrong. Sorry? Yeah. And so that's just kind of generally what happened. I mean, you observe that really is true. But so here this just says that it hasn't gone wrong yet for D equals 5, right? But then it goes wrong for D equals 6. But all those stuff I said about like P being, like you could have a component where the general point corresponds to a subscheme P, which is not a disjoint union of points. We expect by Murphy's Law that to happen at some point. I'm not sure where or anything, but I mean, Murphy's Law will say that that's going to happen. And this problem about the X jumping, I mean, that type of thing, is in principle going to happen at some point. But so it's a complicated situation, you might say. But it seems like, I mean, I think in algebraic geometry, it seems like we're supposed to be looking at this type of thing. I mean, I don't think we should be happy with a statement that says, you know, for C2 bigger than some possibly calculable but kind of big bound, then it's irreducible and good, and so we're happy and we go away. I mean, that leaves a gigantic space of stuff in there where we don't know what happens, right? So it seems like we should be looking at what happens. But of course, life is not necessarily very easy. So let me now, so that's the end of that segment. Let me kind of transition to the whole Higgs bundle segment, which is our next topic. Luckily enough, and thank you for the very nice talks, Oscar's nice talks in biology and our talks this morning, which introduced a lot of the stuff which I should have defined, but so I'll be able to shortcut a little bit. But let me to transition, before giving the general definitions and stuff like that, so the Dolbeault setting. I.e. Higgs bundles, you know, Hitchin's equations. And Higgs bundle. Let's just consider an example. So we're kind of jumping ahead of ourselves, but you'll see it's kind of related to this previous consideration. The kind of canonical example what's the canonical example of a Higgs bundle on a smooth variety X? I would claim that the most unique example of a Higgs bundle is the following thing, is E equals omega 1x plus OX. And phi is just the map from omega 1x into OX tensor omega 1x. And now, so there's some question. So when, I mean, you might say some kind of question about when is this going to be stable? Or semi-stable. Okay, but assuming it is, so at least so let me just point out here that there's a subsheaf which is the one preserved. Let's see did I do this right? Yeah. There might be a subsheaf. Well, there might be a subsheaf here which corresponds to a line bundle plus OX, but that's why it's difficult to decide whether it's stable. But the basic subsheaf is OX containing E, which has the slope 0. So stability, we would have, if any kind of stability, we would have mu of E is negative. In other words, degree omega 1x is negative. Okay, so this is some kind of general type thing. So if this is going to be stable, then your canonical bundle should definitely be. Oh wait, what am I saying? Positive. This is the quotient. Sorry about that. This has slope 0. That's the subsheaf. So the total mu should be positive. So the degree of omega 1x should be positive. So well, without discussing this, which is a little bit more complicated, but let's suppose it is. Then the Bogomolov-Gieseker inequality, which holds also, as I'll be saying in a minute, what does it say? It says that C2 minus R plus 1 over 2R times C1 squared of E is greater than or equal to 0. So suppose dimension 2 R is the rank of this Higgs bundle, which is n plus 1. Okay. Yeah. Okay, so in this case, is equal to 3. Okay. So then the Bogomolov-Gieseker inequality says C2, but C2 of this bundle equals C2 of the cotent, C2 of omega 1x, which is C2 of x. And C1 of this bundle is actually, it's C1 of omega 1x, which is minus C1 of x, right? But square is, of course, the same. And the Bogomolov-Gieseker inequality says that that C2 minus R plus 1 is therefore 4, divided by 2R, which is 6, times C1 squared, is positive. So it says 3C2 bigger than or equal to C1 squared. Okay. So this is the classical Miyaoka-Yau inequality. Of course, I mean, that's not a proof of the Yao inequality until you treat this question about stability. But you can actually do that. I did that in my thesis. You can get a new proof of the Yao inequality. And in case of equality, then we have a projectively flat Higgs bundle. And this actually gives the uniformization of the surface. So you can use this, of course, you're still solving nonlinear PDEs and so on, but I might claim that they might be a little bit easier than the ones you need to solve to do the Kähler-Einstein metrics, possibly. We've kind of seen the proof, roughly speaking, so far. I mean, one of the main steps was done by Yao anyway, but I guess you can. Well, I guess you can use Donaldson for surfaces. You can use Donaldson's first paper about Yang-Mills on surfaces. So now, why is this sort of halfway between my previous geography discussion and the Dolbeault discussion? Well, let me just point out the following thing, which is that Rouleur and Urzua I think Annals of Math 2015, they showed that there exists surfaces with C2 with, like, what is it, let's say, maybe C1 squared divided by C2. With some dense, and their actual theorem says that there are surfaces with giving a dense set of values between 2 and 3 for this amount, which are simply connected. So I remember that Hugh once asked me this question. He said, okay, if we have a surface uniformized by a product of two disks, then it has C1 squared equals 2C2. And for C1 squared equals 3C2, we know that it's uniformized by a ball. So he said, well, so people are wondering, does the surface have to be non-simply connected in between those two bounds? And this theorem says definitely not. I mean, there's definitely tons of surfaces that are not simply connected between those two bounds. And in particular, C1 squared over C2 could be arbitrarily, the slope, could be arbitrarily close to 3. So you might say, what's going on here? So some kind of general question. So in the spirit of my drawing about the church, about the circus tent, what might possibly be going on here? So I think you could ask the following question, which is that, would it possibly be true that maybe this Higgs bundle has metrics in these examples which look close to being flat? So that the surface looks, and hence the surface looks non-simply connected. So what might it mean to have a surface that looks non-simply connected? Right? You might have a surface. What does it mean when something is non-simply connected? It means you can, like, you leave from your house in the morning and you walk around some path and you tie a string to your house, and then you unroll the string as you go around the path, and then you go back to your house and you have the string. And then you start pulling the string. If it's simply connected, it means that some way you'll be able to pull this string back and collapse it all back, right? So what would it mean to be geometrically not not very simply connected, but not all that simply connected. It just might mean that it's really, really hard to pull that string back to your house. Like you might have to like go out and fix a lot of problem, move it even farther away and everything. It's kind of like untying a knot. I mean, you can have a piece of string that's an unknot, but it's so messed up that to actually unknot it, it's kind of not very easy. So this is kind of a question. I don't know. This is just like a philosophical question. But I thought you might be interested. And we could maybe make a more formal statement about that. So maybe it might have a bad constant. So for example, might have a bad isoparametric inequality. In other words, that the area for a loop, the area of a bounding disk, of a disk that is boundary, the area of a contracting disk, is large. With respect to the length of the loop. You might have a short, maybe the string wasn't very long, but in order to simply connect it back to the trivial path, you had to like move it along a large disk. So, but that's kind of, I think, a bit of a guide. So, and we can also ask in these examples, is there something like that happening? So are there some, in the cases where the C2 is going to be small, as we saw from yesterday, the bound, tells you that the L2 bound of the curvature is going to be small, in some sense small. Not as big as it would have to be. So you might have you'll have a connection whose curvature is not all that big, you might say. What is that going to mean? That means you might have, if you have a loop whose holonomy around that connection is a non-trivial matrix, well, even if it's simply connected, when you squish the loop back to the origin, then you're adding up all the curvature terms, as I said at the start, you're adding up all the little curvature terms over that disk, right? But if the loop had a non-trivial, had a big holonomy matrix, then to get it back to zero, to identity holonomy, means you had to add up a lot of curvature terms. If the curvature is small, it means that disk had to be really big, basically. So I think there's maybe some kind of geometrical picture like that. That could be related to this question about geography and so on. Oh, let me just start over here. Or just start the Dolbeault picture. So we've already actually pretty much seen the proof, so let me just state the theorem. So X, let's say, is smooth. Suppose X is smooth and projective for simplicity, and suppose that the Kähler form comes from O of 1 and so on. So we've seen this definition many times already, but let's just write it down. So a Higgs bundle is a vector bundle E, and a phi going from E into E tensor omega 1x. And in the higher dimensional case, you have to add the condition phi wedge phi from E into E tensor omega 2x equals 0. This is some kind of vestige of the curvature condition. Then we'll say this stable or semi-stable. So in fact, in the higher dimensional case, we also need to consider subsheaves, not just subbundles. So for all let's say reflexive subsheaves. Let's say saturated subsheaves. I think I wrote this formula down, so let me just not write it down. The slope is just the degree divided by the same formula. This is the same formula. But what we have to say is that subsheaves preserved by phi. So subsheaves in the category of Higgs sheaves. That's stable. And semi-stable is same with less than or equal to. And polystable is a direct sum. I was making some mistake about this polystable thing. It's easy to make a mistake when you get to this point because because the slope, we're in higher dimensions, the Néron-Savary group can have higher rank, and the slope is only measuring the Néron-Savary, the inner product with the hyperplane class in the Néron-Savary group. So you have to be a little bit careful here. I mean, if you took, you shouldn't really look at, that's not going to happen for our flat case, but you shouldn't really look at things where it's polystable, but just kind of by accident because it's got the Chern class, it's a direct sum of things that have different first Chern classes. They happen to all lie on the same hyperplane. That's not a very good idea, let's just put it that way. Be a little careful. And Le Portier in my seminar Bourbaki said, oh, there's a mistake. And I said, oh, really? In the middle. Anyway, because you have to be a little careful here, okay. Then what's the theorem? The theorem says that if E is semi-stable, let's just say that the C1 of E, to avoid this type of thing, equals 0. Oh, I gotta make this mistake here. Let's just say stable here. Problem. If E is stable, then sorry. Stating the theorem before, I'm getting ahead of myself here, but let me state the theorem anyway, but sorry, I'm getting ahead of my notations here. If E is stable, then E has a Hermite, well, I'll say that what that is in a minute. And the corollary is that delta of E is the delta invariant is positive. And if E is stable and C1 equals 0, let's say Néron-Savary X tensor Q, and C2, but you only need C2 of E intersected with omega to the n minus 2 equals 0. Maybe I should say this is delta of E dot omega n minus 2. So this is basically, so in the case C1 equals 0, then the delta is the same as the C2, and this is the case of equality. Then the metric is flat. See below. And the converse is due to Corlett. Higgs bundle, yeah, E phi. Yeah. I'm going to say that's why I say I was getting ahead of myself. This is the Higgs thing. Sorry about that. I got ahead of myself to state the theorem here. I thought, let's because of time question, I thought let's state the theorem before doing anything else. The converse says that any flat connection comes any flat, GL R C connection. Arises this way. And of course, what's the lineage of the theorem? It comes from the Narasimhan-Seshadri. And everybody that I was saying yesterday. And then, of course, the main person is Hitchin. Hitchin for the case of curves. And rank 2. Hitchin's proof in arbitrary rank. Hitchin's proof is basically going to work in arbitrary rank. You need maybe an extra lemma or something like that, but he wrote it in the case of rank 2. And the converse was also Donaldson for the curves of rank 2. So now I need to explain what's going into the statement here, which is what's the deal with the metric here. How are we doing for time? I don't know if there's something that's blocking the time here. I think the answer is no. I also wanted to motivate this whole picture, but let me first say what the picture is again on the basis of let's do our time thing first. So what are the definitions? So the definitions are that we define, so this is really extremely formal, in fact, once you understand what's going on. I'll explain how to understand what's going on also in a minute. But once you understand what's going on, this is extremely formal, which is that, well, let's just define D double prime. Instead of being the del bar operator, it's the del bar operator of the bundle plus phi. So it's just everything that you have. The D double prime is everything that you have to start with in our current holomorphic world. Okay? That's why this is called Dolbeault. I mean, that's why Dolbeault is one possible word for this. It's because we're starting with a completely holomorphic world. Then we're moving towards the topological world. Okay? And so this D double prime is everything you can have in the holomorphic setting. Okay? In the case of a bundle, the only thing you had in the holomorphic setting was the D bar operator of the bundle. Okay? They happened to have type 0, 1. Well, now we have this plus phi, which has type 1, 0. But we just include that, everybody, in the stuff we already have. Okay? And now there's a similar lemma, is that for any metric H on the bundle E, there exists a unique operator D double prime H, D prime H, which should be del H plus phi bar H, such that del H plus del bar is an H unitary connection. Now, so what's going, there's kind of a subtle, I mean, not all that subtle, but there's a little bit of a game of sign changes in this world. And you have to, and the sign changes all kind of work together and come out and cancel out at the end and give you the answer you want, you might say. But there's a reason for that, which I'll explain in a minute. There's like a fundamental reason why that type of thing happens. But so in this sign change world, we're going to say phi bar, that's the thing that goes with del H, plus phi. Sorry? The phi bar depends on the metric. It's the adjoint of phi for the metric, plus with a sign or something. But the point here is that this is an anti-preserving endomorphism. I mean, so what does this mean? It means that if you tried to use this to add to a unitary connection, you'd be going in the direction orthogonal to the unitary connections. Okay? Right, so you can write down what the definition if you want, but what this means is that this is moving in the opposite direction of any kind of deformation of the unitary connection. Like think of just the complex line. I mean, the unitary thing is we're rotating. Right, there's matrices that rotate. Then the anti-unitaries is matrices that expand and contract. Okay. Then we define DH, this is the connection, is just DH prime plus D double prime. And the curvature is DH squared. And that makes, now everything is well defined, I think, if I'm not mistaken. Now everything that enters in here is well defined, okay? So that's the curvature. And when I say flat connection, that means that DH is flat. And really, the proof of the so there's an observation, like a main observation here. The main observation is that the Kähler identities, with this choice of signs, and types of the forms, the Kähler identities, the order 1 Kähler identities are the same. So it means that if we take, so that says that if we take D prime star is equal to some constant, which unfortunately let's just guess here. Let's put a square root of -1 here, and then so I might have interchanged those signs. Okay. Sorry about that. I should have looked that up, but we were at lunch and everything, so yeah. Anyway, but it's one of the two signs. I mean, there's the square root of -1 and a minus square root of -1, and one goes here and one goes here. But it's the same signs that you use if you put del and del bar. Okay. The classical Kähler identity, you say del star equals -1, the commutator of lambda with del bar, and so on. And the point is that there's an opposite sign here. There's a change of the signs because, right, this is a certain type of form and this is the opposite type of form, so that changes a sign. But we made a change of signs, and we made a change of the type of forms because we included a 1-0 thing inside this thing which was originally of type 0-1. But we also had a change of signs because of this anti-H preserving thing. Those two things cancel out, and they make it so that if you just formally write down these operators, plug them into the Kähler identities, then it's exactly the same identities. And the conclusion of that is that so we can define like Laplacian D is equal to D star plus D star D. This is equal to 2 times the Laplacian del D prime, which is 2 times the Laplacian D double prime, which is by definition D double prime star plus D double prime star D double prime. This star thing, I mean, this is the adjoint of wedging with omega, and this star thing is the adjoint operator in terms of the Kähler metric. But if you look in Griffiths and Harris and so on, that's all there. And so the conclusion is that, in fact, the identical same proof as for vector bundles proves this theorem. So there's really no work to be done. I mean, so that's, that was partially why I was interested in coming, kind of boiling down the proof for vector bundles into a kind of understandable way and so on, to be able to understand that if you just plug all these formulas into the proof, it just works the same way. There's maybe a little, you might, if you try to do this on your at home, you'll notice there's a little glitch, so you need to be a teeny bit careful because the curvature doesn't have type 1,1 anymore, so you need to be a little careful when we do this thing with the Hodge-Riemann bilinear relations that we did yesterday. But that works out well. That's the same principle about the change of signs and stuff works. So that's how you get the proof of the theorem. And so in particular, I mean, this is just a vast generalization. Vast, not all that vast. It's a generalization of Hitchin's theorem. For curves. Then I should say that also, more recently, Takuro Mochizuki proves, among other things, the corresponding statement for parabolic Higgs bundles on X comma D, where D is a simple normal crossings divisor. And it corresponding to flat bundles on X minus D. These are his papers that are called the Kobayashi Hitchin correspondence. Etc. 1 and 2. So we can feel that in principle we have a Dolbeault picture for local systems. Let's see. So I did promise you guys, although how are we doing for time? Oh, okay, let's do that. I promise you guys a bit of an explanation. But let's do the Hitchin fibration. But that's going to be a bit of an explanation. So let's do a little bit of motivational stuff here. So in the proof, in the original proof of Narasimhan-Seshadri, one calculates the deformation spaces on both sides of the map from the set of unitary local systems. Let's say irreducible, maybe. Mapping to the set of stable bundles. Okay. And here the deformation thing is H1 of X with coefficients, so this is in the case X a curve. H1 of X with coefficients in endomorphisms of V, rho, then some kind of real subspace. You might say it's really imaginary, but I times R. Then this thing is H1 of X with coefficients in endomorphisms of E. Okay? So E is the bundle. So the local system is V rho, and this is E. But in the C-infinity sense, they're the same bundle. They're the same C-infinity bundle. And in fact, in this case, there's no Higgs field, so the holomorphic structures are the same. This just has an additional connection. And the point of the whole thing here is that there's a Hodge theory. So we saw the definition of a Hodge structure. So these things have a Hodge structure, have a real Hodge structure. So this is part of a real Hodge structure. So if we take, let's call this like T or something, for tangent space. So TR, tensor C, has a decomposition into T. Let's not call this T. What kind of letter shall we use here? Let's call this L. Okay, for want of a better word. Okay. Okay, so just because of the fact that this is just cohomology of really an orthogonal cohomology of a real local system that has an orthogonal metric, that has a symmetric. And so, as I was saying to some people, if you understand the proof of the Hodge theorem, and if you think of it as a local problem, I mean, it has to kind of be a local problem in some differential equations and stuff like that. You have to solve the Laplacian and so on. But there's 100% no reason why that same proof for constant coefficients would not also work for coefficients which are only locally constant, but you still need a metric and stuff. Okay, so coefficients that are locally constant, a real vector space that has a metric on it, but maybe when you go around, the metric comes back to different, but your local Laplace equation doesn't care about that. So there's 100% the same proof. Okay, gives you the Hodge decomposition. So it tells you that cohomology classes are represented by harmonic forms, and we have this Kähler identity. Right? Luckily, this is still here. The Kähler identity. This exactly says that harmonic forms for D are the same as harmonic forms for D prime or D double prime. But these ones in this case decompose, right? This operator in this case, not in the general case, but in this case, the operator preserves the Hodge decomposition, Hodge type decomposition. So harmonic forms are going to decompose into 0, 1 part and 1, 0 part. And those are going to be representatives for cohomology of the Dolbeault cohomology. So this is going to be H0 of E tensor omega 1x. This is going to be H1 of E, ND. Just H1 of ND, okay? And this is a Hodge structure in the sense that these two guys get inverted by complex conjugation because this is a real vector space. The real thing comes from the fact that we have a unitary local system. And so that means that if you project, right, when you have a Hodge structure, a real Hodge structure of weight 1, that this subspace as a real vector space has the same dimension as either one of these two, right? This has twice the real dimension, and these are two dual pieces. So each one has half the real dimension. So just this piece here projects onto this, and this complex conjugation thing really says that this thing is going to project isomorphically to either one of the factors. And that's the reason why the deformation map is an isomorphism. Right, this is the second factor. Right, this is going to be the L01. Okay. So when you look at it this way, and so it's a little strange, but it's kind of like what we saw about Madhava. It's kind of like what we saw about Madhava. I mean, he kind of invented calculus in 1400 or something like that, but then nobody did anything with it. I mean, so and the same. So I mean, so I think it seems to me like, I mean, but here Hitchin came along, but Hitchin came along like 25 years later or something. I'm not quite sure why you couldn't have at least asked the question at this point, because you could say, okay, suppose I wanted to look at non-unitary representations. Just in an infinitesimal world, non-unitary representations, it just means that if we look at the tangent space of all representations, add a unitary representation, it just means that we're going off here in a direction which is not a real direction. Okay? So when you look at it that way, and in retrospect, it's of course easy, right? In retrospect, you could say, okay, if we wanted to add the non-real directions here, and if we said that the real directions were corresponding to this thing, then it's kind of obvious from this point of view that you should add something here to make it correspond to the non-real direction. But if you had and then to put it in a different way, if you had something whose deformation class on this side was the direct sum of these two things, then you would be able to have something, then you could expect that the deformation class over here was the full complex vector space, which would be the whole H1x endomorphism V complex, which will be the deformation of the complex representation. So that's, you might say, motivation for why, so and then this would be the Higgs field. Okay. So why would you think that, but I mean, okay, I mean, I didn't think that myself. It took Hitchin and gauge theory and like anti-self-dual connections and dimensional reduction of Yang-Mills equations from dimension 4 down to dimension 2 and it's everything until this finally came out, okay. Anyway, okay, so let's see. So why don't we stop this discussion? Sorry, that didn't really explain this thing about these guys, but let's maybe stop that part of the discussion. I'm just saying words. Okay, you can justify. So maybe I should just say it this way: the origin of this idea of writing the operators like that. This is really due to Deligne. For variation of Hodge structure in a letter to Steve Zucker. And see Zucker's papers. So Deligne's letter was, made available to everybody in the form of being the origin for Steve Zucker's paper. So Deligne did kind of what Steve Zucker does in this paper. Deligne did that in the case of a compact variety or a Riemann surface, maybe. And so in the case of variation of Hodge structure, this kind of combination of operators is actually very natural. So in the case of variation of Hodge structure, if you have a family of varieties, you take the cohomology of the family of varieties that has a structure of variation of Hodge structure. And if you say, okay, I would like to recover the cohomology of the total space by taking a cohomology downstairs with coefficients in the variation of Hodge structure, then it's kind of, in that setting, it's kind of obvious that what you should do is combine the Hodge type of the base with the Hodge type of the fiber. That's kind of the explanation for, in the world of variation of Hodge structures, why this term goes into the D double prime. In the case of variation of Hodge structure, these terms both have total Hodge type 0, 1. This has Hodge type, Hodge type on the fiber 0, 0, and Hodge type in the base 0, 1. This has Hodge type in the fiber -1, 1, and Hodge type in the base 1, 0. But the total type is 0, 1. So let's just put it this way. And again, in the case of variation of Hodge structure, you have this thing where the metric has alternately positive and negative definite signs. And that kind of explains this thing. The fact that the flat, for variation of Hodge structure, you have a metric which on the different pieces changes sign, but it's flat. And so if you take the positive definite metric, which is obtained by changing the signs, then the phi, which moves between different subspaces, is going to be an anti-preserving endomorphism rather than a preserving endomorphism. So this stuff, let's not spend too much more time on that, but this stuff is all very well motivated in terms of the theory of variation of Hodge structure. Okay. So let me get to, but I think we'll go a little overboard tomorrow also, as usual. But let me get to the topic that I wanted to talk about today in terms of example. let's kind of jump ahead a little bit. So what about examples? There's like I mean, the situation for curves is amazingly rich, as I think we've seen in Oscar's talks. What about examples in higher dimensions? They're kind of few and hard to come by. I mean, there really aren't too many. And most of the applications that I've been able to find, or other people have been able to find for this type of theorem, have been kind of negative ones that says, you know, if you have something or other, then that can't happen because such and such. So it doesn't really give you examples in some way. Application of the theorem in the higher dimensional case. Sorry. Examples, you know, of Higgs bundles, you know, flat, like Higgs bundles. You can prove that they exist, okay? That's kind of a general thing by taking direct images, so they have to exist, but they sort of don't show up naturally. But so a very nice thing, which is recently, so Dolbeault and Pantev have a beautiful theory of construction of local systems. For the geometric Langlands correspondence. Using spectral varieties. And you might say the amazing thing is where do you get the spectral variety? So you want to construct a Higgs bundle on something or other. So let's construct its spectral covering. Where do you get the spectral covering? You get it from Higgs bundle theory. So let me just explain that, and then we'll stop for today. We've seen, so let me just not give the definitions because we've already seen that several times. So we have the Hitchin fibration. So let's let C be a curve. Then we have the Hitchin moduli space, which is the moduli space of Higgs bundles. I guess we were calling this H, but maybe let's call this, I'll call it B, okay. I think Marino was calling this H, but okay. Which is something like a direct sum of H0 of where I might be. I is 1 or 2, depending. The I equals that. This depends on if you conclude the I equals 1 part or not. Depends on whether you want a determinant trivial or not. I guess we'll be doing trivial determinant bundles. So I equal 2. And now this also has a rational map to the moduli space of bundles. So let me just call this bun, but not a round, but a square bun. Let's see, a bun. I guess we could call this M. Okay, let's call this M. M without the H, that's the moduli space of bundles. Okay. So remember that we've already seen this, that you can write this down by Serre duality fairly easily, that a cotangent vector to M is really exactly a Higgs field for a bundle. So this is a subset, and this actually has a map. But this map from here to here, this is a subset here, but it only extends as a rational map. It's not a well-defined map. That's actually kind of crucial to the story, in fact, but we'll see that maybe tomorrow. So suppose we choose a point here. And let's take y. Maybe y0 is equal to h inverse of the point B. So this is basically, this is an abelian variety, some kind of prim variety. Okay. This is what we saw this morning for an integrable system. These are the complex tori in the algebraic integral system that we have here. These are the Hamiltonian functions. Okay. So now, here's the idea. Again, amazingly simple. So apparently Tomasz Hausel wrote a letter to Hitchin about this in the late 1990s. And also I kind of saw a talk by Faltings. I saw a talk by Faltings where he kind of vaguely implied that this might be the case. And other people, I've heard physicists like Witten say, oh, by the way, there's such and such a thing. So I guess this has been kind of vaguely thought of, but not really formalized all that much. So we have a rational map. We could actually blow this up. I'm getting too down below here, but we could blow up here to make a well-defined map. Okay. And the basic idea is extremely simple. It's just that let's use, so y is basically contained in the cotangent bundle of M. So to get a spectral covering by the Bouville-Narasimhan-Ramanujan correspondence, what do you want? You want to have a spectral curve. You want to have a covering of the space that's contained in the cotangent bundle. And that's exactly what we have here, up to something about blowing up and rational stuff. But basically, we have space that's a covering. This is a covering contained in the cotangent bundle. So Donágyi-Pantev say, let's use y So the idea here is, and they've done that in a paper, in a preprint, which they were writing for years and years, but just came out this past fall. So the idea is to use y, which is, so remember y is the Hitchin fiber, so it's actually an abelian variety blown up. It maps down to the moduli space here by a finite map, or generically at least finite map. We can take a line bundle here and take the direct image, and that's exactly going to be a Higgs bundle. And so the only subtle thing here is that, this is indeed a bit subtle, is that you need to set up a parabolic structure on this bundle. If you just do this, you could try to just do this bundle like that. Well, for one thing, it's really not going to be, this inclusion is really kind of only rational. So the fact that, if you look at what happens here, you're actually going to, the bundle you get is actually going to have a logarithmic Higgs field with logarithmic poles along this wobbly locus. Okay. But if you don't put a parabolic structure on, then you're not going to get the Chern classes to vanish. You might say the big deal, this is irreducible. Since it's irreducible, whatever you're going to define is automatically going to be stable. The big question here is how do you get the Chern classes of this bundle E to vanish? That's, you might say, the surprising thing. I mean, if you just write down a bundle, its Chern classes are.
Is a divisor is not so obvious, right?
Well, in the examples we can do, which are very few, it's pretty clearly a divisor. Yeah.
General result,
I think there is. I mean, I think Christian Pauli maybe, and some, yeah. I mean, it's not too hard to see that it really should be a divisor. It's the place So M actually occurs inside the nilpotent cone. This is for the experts, sorry guys. M is the bottom piece of the nilpotent cone, and W is the place where the rest of the pieces of the nilpotent cone join on to W, to M. Yeah, wobbly means not very stable. It's wobbly, right? It's not very stable, then it's wobbly, yeah. Yeah, I think so. But I don't think it's that difficult. I mean, it's because of the fact that you have the nilpotent cone is Lagrangian. And so you couldn't have a Lagrangian thing if you had two divisors in the nilpotent cone that intersected in a lower dimensional subvariety. I mean, also, the proof is just that that has to be Cohen-Macaulay. The nilpotent cone is a Cohen-Macaulay scheme because it's defined by equations from B. Yeah, okay, I'm not sure. Anyway, in the examples, it's the divisor. It's expected to be a divisor, and many people have proven results like that. Yeah. Anyway, so I should be finishing here. So we'll start tomorrow with sort of a little behind and stuff. We'll start by discussing this a little bit more. Okay, so stop.
Questions?
Well, I have first a comment and then a question. And the comment, when you were saying, in reference to the lecture yesterday about how it took so long to discover this, right? That it took gauge theory and dimensional reduction and so on. But the fact is, as Hitchin actually, it's a historical comment, right? That it was by considering the cotangent bundle of the moduli space of stable bundles that he came up.
That's how Hitchin's proof works in any case.
Yeah, but I thought it was by dimensional reduction because he presents that in his paper like this.
That's how his motivation for the paper. Okay.
That's not the way that historically came. It's a comment that
this was the motivation.
That he came. Yeah, it was the cotangent. Yeah, the cotangent. Basically.
But yeah, he had a paper in Duke about the cotangent bundle, and
indeed, but that is the original motivation somehow for considering the whole thing.
Was this was this the reason why he would think that would parameterize flat connections?
I suppose.
In the usual case, you have an exact sequence, H1xc to H1xo and H0 omega 1, correct? 0 to H0 x omega 1, H1xc to H1o. Okay?
Yeah.
No, yeah. So that generalizes, if you have a representation in GL and C, so the extreme terms will be H0 ND omega 1, H1 ND. And the middle will be H1 of the local system of GL and C representation. So you see the GL and C. This exact sequence is in our paper, but we never realized.
Yeah.
Yeah, you see what I mean?
Yeah, I understand, yeah.
Take the GL and C representation, then
Yeah.
get a local system. Here is a local system homomorph in the middle.
Well, you can also say that the moduli space of the Durand moduli space, I didn't talk about this, but the Durand moduli space is going to be a torsor for this thing rather than just that bundle basically. Yeah.
It's there.
Oh, sorry. So I have a question about when you talk about examples and how few there are and so on. There's this general comment that I don't know if you can sort of put some meat in it and these spaces tend to be rigid, right, as opposed to what happens on curves, right? So can you make some statement of when they are rigid, when they are not, or whatever? So
well, they do seem to tend to be rigid. So I wrote a paper saying that you could construct examples where they were not rigid by taking direct image. So there's a direct. This is like functorial, and in fact, Takuro Mochizuki and Claude Sabat have a very wide notion of functoriality and all the operations and stuff like that for this type of thing. generalized mixed Hodge modules to this setting. So if you have a non-rigid local system upstairs, you can get that like by taking a line bundle or taking a pullback from a curve and tensoring them together and stuff like that. Then take the direct image, you'll get a non-rigid thing. And so Kontsevich has a conjecture or a question or something like that, which is maybe that's the only way of getting an example.
More questions, comments? If not, let's thank Carlos again.